Good morning, everyone. Welcome to our webinar. We're just going to hang on a couple more minutes just to allow a few more people to join, and then we'll get started. Good morning, everyone. Welcome to this webinar from Guru Systems. Today, we're going to be presenting ambient networks, shared ground loop arrays, and heat network regulations for you. Thank you for taking your time to join us today. So the presentations is going to be about 45 minutes total, and that will include some time at the end for any questions that you want to share with us. We're on Zoom today, you're probably familiar with it, but there is a area that says Q&A. If you want to pop your questions in there, Georgina and Jack might be able to answer those as we're going through, or I will be proposing them at the end. If we can't get through them all, or we need to go away and look at some of these questions in more detail, we'll get back to you directly with some of those answers, but hopefully we'll have time today to get through some good questions. So it's being presented by Georgina Orso, who's our head of marketing at Guru Systems, and Jack White, who is our sales manager. The presentation is going to be recorded today, and that will be shared afterwards. So if you have any technical difficulties and need to come back to the video at another point, that will be shared later on this week. So without further ado, I'm going to hand over to Jack and Georgina.
Hello, as Charlotte said, welcome to today's webinar. The session has a title of Ambient Networks, Shared Ground Loop Arrays and Heat Network Regulations, which is a slightly snappier version of the title of a recent white paper that Guru Systems has published, that being, do ambient temperature heat networks or shared ground loop arrays have to comply with the heat network metering and billing regulations? Which is what we're going to be covering today. So next slide, please. This is the white paper I just named. It's a relatively quick read, but I'll be going through the key points today before handing over to my colleague Jack, who will be talking through how we can meter fifth generation networks and the benefits of doing so. So why did we write this? Well, most of us here will know that the heat network metering and billing regulations require heat networks to do things like fit meters, measure consumption in individual homes, and then bill customers living in those homes based on the amount of heat that they use. If the metering and billing regulations are new to you, we've got some great resources on the Guru Systems website. But for now, I'm going to assume a base understanding. So we've got those rules, the requirement to fit meters, measure consumption, and bill the customers living in that home based on the amount of heat that they use. The regulations also include a few other requirements, such as notifying the government of any heat networks that exist. But the main focus of the regulations is that those customers are billed transparently and based on their actual consumption. While some heat networks are explicitly exempt from fitting meters under those regs, such as purpose-built student accommodation, there is a significant grey area we find that really starts with the fundamental question of what is a heat network. So we published this white paper, which looks at the different types of heat networks and whether they're covered by the regulations. Okay, so let's get started. Very basic intro slide. What are the different types of heat networks? I've got 3 types that I'll be talking about. So let's start with the first type. Next slide, please. First up, a heat network with only centralized generation of heat. I appreciate I'm skipping a bit of a history lesson now by not starting with first generation heat networks way back in the 1880s. So when I talk about heat networks with only centralized generation of heat, I'm talking about fourth generation heat networks that we're building in the UK today. These networks have a very obvious heat generator, like a boiler or a large scale heat pump that might be in the basement of a building or in a plant room on the site. Hot water is then pumped around the network, and each dwelling typically contains a heat interface unit, or HIU, which transfers heat energy from that water arriving from the system over to the water or heating system in the home. For fourth generation heat networks, the flow temperature is usually around sort of 55, 60 degrees C. And in the past, central source of that heat was likely to be combined heat and power plant, but today you're much more likely to find a large scale ground source or air source heat pump as that central source of heat. On to the next slide, please. An ambient temperature heat network or ambient loop network works slightly differently to a fourth generation heat network. These can use the network as a heating source or as a heating sink, depending on whether the demand is for heating or for cooling. And the system is essentially a two-stage design. First, we've got a plant room that heats water to around 15 or 30 degrees, or 15 to 30 degrees C, perhaps using waste heat from a data center or a river source heat pump, or some other source of low-grade heat. And secondly, you've got an individual heat pump in each home. So essentially, you've got centralized heat generator, as well as individual heat pumps in each dwelling, which makes use of that thermal energy that's coming from that centralized source. When the system is running in heating mode, i.e. the demand is for heat and not for cooling, the heat pump in the dwelling tops up this heat from the central source to a usable temperature that's either for space heating or domestic hot water. Oppositely, when the network is being used as a heat sink, i.e. it's in cooling mode, the flow temperature from the central plant stays the same, so still around that 15 to 30 degrees C, but the thing that changes was what's going on inside the heat pump, the one that's in the dwelling. So the heat pump in that situation basically changes direction, extracting thermal energy from the dwelling and returning hotter water to the network, essentially acting a bit like a fridge. That heat might be extracted from the dwelling using a fan coil unit, for example. Either way, whether the network is providing heating or cooling, the flow temperature delivered at the dwelling is the same. Almost. Next slide, please. The final type of network that I'm going to be talking about today is shared ground loop arrays. Shared ground loop arrays are different from both ambient loop networks and heat networks with only centralized generation of heat. Specifically, they use a series of ground arrays, typically boreholes, that are used as a heat source by multiple properties. Heat pumps in each dwelling upgrade the heat from the ground array and then output that heat at a sufficient temperature for space heating and water heating. Dwelling level pumps are used to circulate the water through the shared ground loop, and often there are no centralized pumps or plant other than perhaps dosing or pressurization. I need to thank Kenza for this diagram. It's much more colorful than my previous two. Okay, so we've covered three types of networks. We've got one, heating networks with only centralized generation of heat, two, ambient loop networks, and three, shared ground loop arrays. So moving on to this gray area that I mentioned at the beginning, we're going to look at the definition of a heat network in the metering and billing regulations. You might think that traditional heat networks, ambient temperature heat networks, and shared ground loop arrays would all be considered heat networks under the regulations, given that the system is ultimately a network of multiple homes where the primary objective is to deliver heat. Fortunately, it's not that simple. Next slide, please. So bear with me, there's a lot of words on this screen, but I will take you through them. So what we're looking at here is some guidance that BEIS has produced, and I'll go through this now. But despite this guidance, actually, one of the reasons why we published this paper is that we've encountered a number of projects over recent years where uncertainty as to whether a network is or isn't a heat network in the eyes of regulation has led to delays on site or increased costs where designs have to be adapted once the project has begun. And we often see this uncertainty even on ambient loop projects. So let's look at the guidance quickly. We've got three main sections here. The first is around the components that constitute a heat network. The network has to provide a shared source of heat for multiple users. The heat transfer medium must be water, steam, or chilled liquids. The heat must be used for heating and cooling, and hot water use or processes. And the heat must be sold to final customers by heat supplier. The point that I've bolded here is that the network provides a shared source of heat for multiple users. It's one of the key takeaways from this section of the guidance. We've then got some guidance around the technology at the central heat source. This gives a pretty straightforward guidance. It's covering off boilers, it's covering off CHP, and crucially, it's covering off heat pumps as well, where they act as that central source of heat. And then we have a final section, which is around what isn't a heat network, with 4 bullet points. And you can see that the last one says individual heat pumps. Because ambient loop networks require individual heat pumps to be installed inside the home, as well as having a central plant that heats water to between 15 and 30 degrees C, as we mentioned earlier, there is often confusion as to whether these systems do or do not fall under the regulations. We've got a clear network that provides us a shared source of heat for multiple users, but we do also have heat pumps in the home. So when you look at this guidance as a standalone, it can be a bit, well, not confusing, but there's some grey areas there. To our knowledge, no further guidance other than what we can see here has been issued by BEIS or the Association for Decentralised Energy. And because of this, developers, local authorities and housing associations are often left to interpret the guidance themselves, which can lead to the problems that we mentioned earlier around projects being delayed. So I'm going to go and talk through each type of network in relation to this guidance now. So we know that a heat network with a plant room and HRUs in each dwelling is quite straightforward. The plant room or energy center that heats water to a high temperature and is the central heat source, and then it's sold to final customers. These networks, the ones from my very first slide, which has the HRU in each dwelling, are clearly covered by the regulations. And because of this, I didn't give them their own slide. Sorry. So let's move straight on to ambient loop networks, which is what we're looking at here. So we've just outlined the confusion as to whether ambient loop heat networks are covered relates to the fact that the dwelling contains an individual heat pump. But when you look into it, the crucial point to note here is that in an ambient loop network, there is still a central source of heat energy. Yes, that plant room doesn't heat water to the same temperatures as a 4th generation heat network, but the ambient loop network does provide a shared source of heat energy for multiple users. While that ambient heat is then upgraded within the dwelling, there is ultimately a single supplier of heat to all dwellings. So the key takeaway here is that no new heat is produced in the dwelling. The temperature is only upgraded. So all of the heat in that system is ultimately coming back from that central source. Given that, it's widely understood that this type of network is covered by the heat network metering and billing regulations. Shared ground loop arrays, this is where things get even less clear. We're trying to work out whether a shared ground loop array falls under the regulations, or when trying to work out whether they fall under the regulations. The main point to consider is the line from the BEIS guidance we saw a few slides back, which says the network provides a shared source of heat for multiple users. And the key word in that sentence is provide. So yes, water moves around the building, but there is no one provider of heat. The water gains thermal energy in the boreholes, which go deep into the ground, but no organization is generating this thermal energy. If no one is generating, then likely no one is also selling this heat. Yes, there are maintenance costs associated with operating a shared ground loop array, dosing, pressurization, and repair. But all of the work associated with providing usable heat energy is done by that small heat pump that's in each dwelling. And so all costs are paid by the individual running the heat pump in their home. To our knowledge, this explanation has never been clearly stated by BEIS or the Association for Decentralised Energy, but organisations such as KENSA publicly argue for this position. Now, there are risks associated with not fitting meters into these systems that relate to upcoming regulation of the industry by Ofgem, which I'm going to cover next. But for now, shared ground loop array systems are generally understood to be exempt from the heat network metering and billing regulations. And my final point before I hand over to Jack is compliance. So efficient heat pumps in both ambient loop networks and shared ground arrays save customers and building managers money. But there are strong trends towards performance reporting in the regulatory landscape, which we also need to consider. I have 3 points that I want to cover quickly here. The first is regulation by Ofgem. So the heat networks industry, I think we should probably all know, has been preparing for regulation since BASE published their Heat Networks Building on Market Framework consultation back in 2020. Ofgem was then later confirmed as the regulator, and plans to regulate the market were formally introduced as part of the Energy Bill in the summer. While details are still being finalised, regulation is ultimately expected to give heat network customers equivalent rights to those who heat their home using gas. And following publication of the Energy Bill, BASE confirmed that protection for customers will also include technical standards based on the minimum requirements of CP1 2020 to deliver ultimately the principle that heat network customers should be protected from the costs of poorly performing heat networks. Given ambient loop networks are widely considered heat networks under the heat network metering and billing regulations, as we've just covered, it's quite a straightforward conclusion to say that they'll be considered heat networks by Ofgem too, and so these technical standards will apply. CP1 2020, so we've just mentioned this, the Heat Networks Code of Practice 2020, published by CIBSE and the Association for Decentralised Energy, CP1 2020 as it's more commonly known, is a comprehensive document that outlines how to design, build, and manage well-performing heat networks. It's not a legal requirement to follow this, but it is strongly recommended. And with Ofgem using it as a basis for these technical standards, I think it's prudent to consider it as fairly mandatory. CP1 2020 is, I think, 229 pages long, and it's a full, has a full list of the do's and don'ts for heat networks. But Annex C, which is called Measuring Performance, outlines what kind of data should be captured to support an efficient network as it moves through into operational stage. So I'm quoting from page 181 here, and I have this written down so that I don't mess it up. But it says in relation to capturing data from a heat network, that furthermore, the AMR system should be able to record, transmit, and store the following information at least a half-hourly basis. That's meter read, flow rate, meter read, flow temperature, return temperature, flow rate, instantaneous power. So that's in Annex C there, which that's in Annex C, which states what ultimately you should be looking at when you're capturing data from a heat network, getting those performance metrics. And then you've got best practice point, BP 3.8C, which goes a little bit further, obviously because it's a best practice point, says that capturing data every half hour, goes further than capturing data every half hour, and states that you should select meters and a meter reading system that are capable of providing meter readings at 5-minute intervals to give residents / customers and the scheme operator even greater granularity, and hence allow more informed analysis decisions about control settings, end quote. So we agree. We think that capturing data every 5 minutes allows you to spot problems when a heat system is in different modes, such as domestic, hot water, space heating, or standby. And if we're looking at what this means for ambient loop networks, 5-minute data is the most reliable way to estimate coefficient of performance, or COP, in heating and cooling modes separately. Jack will talk about COP in a moment. And thirdly and lastly, I just wanted to mention the London Plan Policy SI2B scene, which affects developments only in London. The Greater London Authority has set out a requirement for all major proposed developments to monitor and report on their actual operational energy performance for at least 5 years. Without this, planning consent may be at risk. This requires heat suppliers to go beyond the requirements of the metering and billing regulations and collect and report on heat network performance data regardless. Okay, so that's my section finished. I hope you have a clearer understanding of what is and isn't considered a heat network under the regulations, but why monitoring networks regardless is a sensible decision, considering these compliance considerations. I'll now hand over to Jack, who's got more to say.
Thank you, Georgina. So, hello everyone. So Georgina's just taking you through all the background of the different types of heat networks. So now it's my turn to talk a little bit about what that means in practice. Then we're going to have a look at how you would go about monitoring an ambient temperature system, including that heat pump in the dwelling. Then I've got some data which shows the difference between a poorly performing system and a well-performing system. So in terms of what it means for the cost to the resident and the cost to the operator. So whether it's a legal requirement to meter or not, in Guru's experience, unmonitored systems do not perform well. Poorly performing systems cost more to run, and then these costs are invariably end up being passed on to the residents, or or it comes out of the bucket from the landlord. So none of that's good. Guru's systems, we see this all the time with traditional heat networks. So in fact, the graph that we're looking at now is from Guru Pinpoint. It sums up pretty well what I'm talking about. So just before we go on, the graph, what we're looking at here is the y-axis. We're looking at delta T, so temperature differential, and then we've got over time across the bottom. You can see there's a trend sort of going down over time. So here we've got a network in London that we worked on a few years ago. So what you're looking at is the slow decline of delta T in the plant room over about a year and a half. So delta T is the difference between flow temperature and return temperature. And generally on a fourth generation heat network, you want this to be as high as possible. So to have as big a gap as possible, basically. This was actually a site where a load of work happened, a load of performance work happened a few years ago. But over time, if you follow the graph, the delta T drops from around 25 degrees, pretty much down to 0 degrees, only after 18 months. So the zero delta T means that water is just continuously rushing around the network, and it's got limited use. So it usually means really eye-wateringly high bills for customers too, and hot corridors and loads of bad stuff. Pumps running flat out, all the stuff that you don't want on a heat network. But in fairness, this heat network did used to perform really well. At the beginning of its life, it was performing great. But because it hasn't been looked after, the problems have arisen. And we see this all the time, even where networks are really well designed and probably commissioned before residents move in, unmonitored heat networks are often left to drift, with performance degrading over time. And I think this is compounded with heat pumps included now, because an HRU kind of operates in a relatively similar way to a boiler, whereas a heat pump it's a different way. It's a different way of heating and cooling your dwelling. So there's very little knowledge. So there's a big learning curve for homeowners and customers. So the decline isn't usually the fault of one thing, one major component. It's usually the accumulation of really small changes in the system over time. So, for example, maintenance engineers coming to site and fixing, rectifying an issue, but without regard for the effect on the whole system. And we see the exact same trends with boilers and in heat pumps. Unmonitored heating systems just don't perform well. Bad news is, to date, no detailed performance data from an ambient temperature network or a shared ground loop has been published. This is kind of concerning because you can make a safe bet that we'll be seeing similar trends to this. And there are a lot of these to come. We're seeing an awful lot of these in design phase at the minute. At Guru, we would argue that capturing performance data from a heating system leads to better outcomes for customers over the lifetime of the development. And as always, retrofitting meters after residents complain about high bills is much more expensive than fitting meters up front, and the disruption, nobody wants it. So next slide, please, Charlotte. So how do we do it? So 4th gen heat networks are relatively simple things to monitor. Ambient networks are there's a few extra things to think about. We'll go into that now. Next slide, please, Charlotte. So on this diagram here, we've got some greyed out bits, and we'll come to those on the next slide. This is because we're going to break it up into sort of different levels. I suppose we're going to have basic level to what we think you need to comply with heat network metering billing regs. Then we'll have advanced performance monitoring as level 2, and then level 3 we're going to be looking at a really rich information that comes out of the dwelling for diagnostics and and some other good stuff. So this diagram here, we're focusing on the most basic level. So this is what we think that you need to install to comply with heat network metering billing regulations. As we've covered earlier, ambient loop heat networks are widely understood to be heat networks under the heat network metering billing regs. This means that all final customers of the network must be billed in line with their consumption. To do this, you need to capture consumption data. So that's kilowatt hours of consumed heating and cooling. The really important thing to mention here is that you need to install a meter and a meter reader that can capture data from the 2 registers. So we've got heating and cooling coming out of the ambient loop. There's kind of a load of magic that goes on in a heat pump. So heat and cooling is both taken from the flow temperature of the ambient loop. But what it will do, it will either return a positive delta T or a negative delta T, and the heat meter is installed on the return pipe going back into the ambient loop. What you need to make sure is that meter has got 2 registers that will automatically switch over. And not all dwellings will have heating and cooling in them, but we're seeing more and more that are. So you just need to make sure that meter has got the ability to capture both, because quite traditional thermal energy meters will have a single register just for heat, so any cooling will be missed. And then on top of that, you just need to make sure that the meter reader will also have that ability to read the 2 registers inside that meter. Okay, so yeah, so thank you very much. So for capturing kilowatt hour data for the heat network metering billing regs was level 1. This diagram shows level 2 and 3. So the diagram on the left is for, let's talk, that's the advanced performance monitoring. So here we've also included an electricity meter, and the electricity meter is dedicated for the heat pump. So capturing data from both the heat pump, from the heat meter and data from the electricity meter means that you can calculate the coefficient of performance for that heat pump. We'll come on to why understanding the pump performance is important shortly, but first let's look at how we do it. So we might want to calculate the COP, the COP in heating mode and the COP in cooling mode separately. To calculate the COP in heating mode, it's heat output, kilowatt hours, divided by electricity input, kilowatt hours, while the heat pump is in heating mode, i.e. when the delta T return is positive. And then to calculate the COP when the heat pump is in cooling mode, it's cooling kilowatt hours divided by electricity input, kilowatt hours, while the pump is in cooling mode, i.e. when the delta T is negative. If anyone's got any questions around this, if they want to go over it in more detail, please, I'm here after the show. So by setting up the situation on the left, that is connecting your meter reader to the thermal energy meter and the electricity meter, you can comply with the heat network metering and billing regs and stay on top of the performance of any heat pumps on the site. And then the diagram on the right shows this is the sort of top tier monitoring. So this would be a direct connection, machine to machine Modbus connection to the heat pump itself. So we would use Modbus in most cases. This can help us extract things like fault codes for remote diagnostics of issues. And then it also means that you can carry out interventions on systems remotely too, so changing set points and so on. And actually this connection may even allow you to mitigate the electricity meter in the previous level, because a lot of heat pumps already have electricity meters built into them and carry out their own clock calculations, and that can all be extracted from this Modbus connection too. Okay, so that's that one. Thank you. So what's the point of monitoring monitoring the ambient loops? Next slide, please. So whether it's a legal requirement or not, in Guru's experience of monitoring more than 250 heat networks across the UK, unmonitored systems just don't perform well. Poorly performing systems cost more to run, and these costs invariably are ended up passing on to the residents. We see it all the time with traditional networks. So we're talking about traditional networks just because there aren't many of the ambient loops in the wild at the minute. So networks that capture and act on performance data to keep operational costs low, even when networks are well designed and properly commissioned before residents move in. Unmonitored heat networks are left adrift with performance degrading over time. This is often not due to fault in major equipment, as we discussed earlier, but an accumulation of small changes over time. For example, engineers turn up to site and just making some small changes. That just it just adds and adds and adds and adds to the issues. So real-world monitoring of heat networks over the last 3-year period, which is a project that we carried out with the UK government, showed that the cost of heat and carbon emissions can more than double on a heat network within 3 years if actions aren't taken. And to date, no detailed performance data from an ambient loop network has been published. However, it's clear to see the impact of inefficient heat pumps on customer bills through some simple modelling. So the chart on the left here shows the cost of electricity to power a heat pump generating 4,000 kilowatt hours of heat per year at different coefficient performance levels. And if we just want to have a quick look at the chart, so the y-axis on the left is total cost per dwelling for heat. The y-axis on the right is electricity consumption, and then the x-axis we're looking at different coefficient performance levels. And these bars are annual levels. And then the bars, you can see we have the blue part is the cost to run the heat pump, so that's the electricity cost. And then the yellow part is the estimated share of the cost coming from the central plant, so actually from the ambient loop. And we can see that's not actually an insignificant amount there. So we've used, so 4,000 kilowatt hours is relatively low compared to the average UK household, which is more like 3 times that. But this is more representative of what we're seeing for heat consumption that we see on 4th gen heat networks. So, in high density dwellings. We've used the October 2022 price cap to show the varying costs to the customer. And we've chosen 4,000 kilowatt hours here because that's Ofgem's middle scenario for heat consumption from a gas boiler. But regardless of the amount of heat consumed, you'll see the same curve. So heat pumps with the lower COP require a lot more electricity to meet the heat demand requirements than the heat pumps that are more efficient. So you'll see plenty of bold claims from the manufacturers about expected COP of their heat pumps. It's important to be able to hold these claims to account. Because on the ground, heat pumps can often work much less efficiently than expected. And, I mentioned it earlier, they just work differently to traditional heating systems. Users are unfamiliar. So for context, the chart on the right, this one's there's quite a lot of information on this chart, but what's probably worth focusing on here are just the little squares, the little different color squares. So this is a sorry, I've just lost my place. Okay, so for context, the chart on the right shows the performance of a variety of different heat pumps in different homes in the UK. This data is from an energy saving trust study, which looked at COPs of heat pumps. In phase 1, the little square shown in yellow, the COP of each heat pump was recorded, and in phase 2, A number of interventions were taken following analysis of the performance data captured from each heat pump. And then after these interventions have been completed, the COP was recorded again, and that's shown in this sort of orangey red colour. And what you can see is that generally, particularly where interventions have been carried out, the darker orange squares are providing a much better COP for each heat pump than previously when no interventions were carried out. We could spend lots of time looking at this study, but we just don't have time today. The thing to note here is that the average performance of a heat pump is much lower than the COPs you see commonly quoted by heat pump manufacturers. Often a manufacturer will quote 3.5 or more, but here we can see that the performance is much closer to a COP of 2. This can be improved by data-led interventions, but the point I wanted to get across here is, like all heating systems, heat pumps can fail to deliver on their promise due to errors in design, commissioning and operation. Without capturing electricity data as well as the heat meter data, you risk finding out that there are problems from customers when they see their bill, rather than scheduling proactive maintenance to solve problems before they impact customers. And as with just general fourth gen heat networks, there are so many stakeholders involved in this, and we're not bashing manufacturers or specifiers here. It's just that things can easily go wrong because the whole process of designing, installing, commissioning, maintaining a heat network is quite fractured. So data is key. So next chart, please. Next chart. So it's just, in a nutshell, it's just going to lead to lower operational costs. So if you monitor it, you can spot problems and inefficiencies. You can carry out minor, major interventions that will lower the consumption and reduce call-outs, reduce carbon output, and it's as simple as that. Next slide, please. So Georgina mentioned a white paper that we recently published. There's quite a lot of information in there. It's still kind of a short read, but it's got everything that we've covered today and more. If you would like to get a copy of that, you can go directly to our website and download it, or you could also just email me or any of my colleagues, and we will happily send you a copy. So that's the end of the presentation and webinar, and we're just going to move on to some questions now.
Thank you, Jack. Much appreciated. So if anyone has questions based on what Jack and Georgina have covered, whether that's to do with the regulations or the different type of heat networks, heating systems that we've covered today, please pop them in the Q&A and I can go through those. So we have a couple to go through. I'll start off initially with, can you tell us which energy meters have heating and cooling modes?
Yeah, that's me. So I won't talk about manufacturers now because there are a few. The most important thing to look for, and if you want to contact me directly about that, that's absolutely fine, and I can share a list of the meters that we know will work. But when you're looking at the specification of the meter, you just need to make sure that it has heat and cool out of the box, so pre-configured in the meter. So as an example, now hopefully I'll get this right, if you imagine you've got the ambient loop and your supply temperature to the heat pump is 20 degrees, in heating mode, I'm just making some numbers up here, we might be return coming out of the heat pump, it might be 5 degrees. So we've got a negative delta T there of 15 degrees. Well, that's fine. In a normal heat meter, that's exactly what it's set up to do. If it's in cooling mode, well, you can have a positive delta T because it's still taking 20 degree temperature into the heat pump, but it's actually going to be returning at 35 degrees. So you need to make sure that the energy meter will be able to automatically switch over and register. And then on top of that, you also need to think about the meter reader that you've got connected to it for your automatic meter reading system. that meter reader needs to be able to see both registers on there, and this will 9 times out of 10 be an M-bus type meter. So the meter reader should be able to interrogate the registers of that thermal energy meter. I think that's it.
Thanks, Jack. Another one we have is, what would typically cause a heating network to lose efficiency?
I can take this one, although Jack, feel free to chip in, because I know it's something that you talked about in the presentation. This was something, well, I'll try and build on something that Jack was talking around those small changes to a network over time that perhaps don't do one big action that knocks something off, but that has a cumulative effects over, say, a number of months. What we see like really, really often when we're looking at poorly performing heat networks is that loss efficiency is ultimately related to a maintenance engineer perhaps going in to fix a problem for a customer. Perhaps there's been a complaint that goes into the heat network operator around something like the speed at which hot water comes out the tap, and a maintenance engineer will go in and solve that problem, but in isolation of perhaps looking at the whole system. So you might get a maintenance engineer who turns up an HIU to the max so that we can really deliver that nice hot water for a customer. The customer's super happy, but then what's happening in the background is that perhaps just to meet that demand in that one flat, there is a very high flow rate of warm water heading towards that dwelling. Very little of that energy is being extracted, and so then you have huge amounts of warm return return water coming back to the energy center. Often the quantity of that warm water is what is much more than the quantity coming from many other HIUs in the system, and so then back at the plant room you will see an overall uptick in inefficiency just because perhaps that one flat, if that happens a couple of times across a network, you're suddenly looking at a volume weighted average return temperature, which is much higher and causing the system to be more efficient over time.
Thank you, Georgina. I was going to stick with you because I think this one is probably regulation related. So for you, so when do we expect Ofgem to begin regulating the industry?
That's a great question. It's not one that I have a definitive answer to yet. So I think initially we were expecting around 2024 as the timelines, but obviously the energy bill has been delayed this year. It has restarted, it's back going through Parliament now. So expecting a delay, but not quite sure at this point when that whole process is going to be concluded. I do think that they're going to be announcing more detail on these technical standards that I mentioned earlier relatively soon when they put that information out in the summer. I think the commitment was to publish something within a year, so hopefully seeing something soon around technical standards.
Amazing, thank you. Slightly more technical, complex question. I don't know whether we've got time enough to answer it here, but regarding the system SEOP scope for ambient loop, and whether it would be combined heat outputs from all dwelling heat pumps divided by the sum of combined electrical inputs to all central heat pumps and dwelling heat pumps.
Thanks for the question, Stuart. I had to read it through a few times, I think, to get my head around it. And I think what I'm going to have to do is take it away, but maybe it might be helpful if you can write something in the chat. Is the aim of your question to get to a seasonal coefficient of performance, like one figure for the whole network, or are you looking at something different? Because I know that when Jack was talking about metering for COP, we're looking at kind of in like the COP of, say, for example, an individual heat pump in the dwelling, and then separately counting the calculating the COP if, for example, it was a heat pump that was that central source of power, central source of heat even that's going in. I think your question is around trying to merge those two those two figures, but what I think, so because of that, I've actually not come across this situation before. So what I'm going to do is take it away and go chat to the team, but I'll drop you an email to answer that one.
Excellent. We are actually almost out of time. So I am going to leave it there. So Stuart, we'll get back to you, and Ivan, we haven't managed to get around to your question, but we can get in touch with you via email and answer your questions about the billing structure of these systems. So I'd like to thank Georgina and Jack for today. Thank you for your time, and thank you to everyone who joined us, and we'll be sharing the recording of this in the coming days, so keep an eye out for that.
Thank you, everyone.
Thank you.